Hey, welcome. We're going to be doing single phase transformers today, and we're really going to be looking at a couple of operating characteristics of the transformer and sort of hopefully cementing the concepts of uh, the turns ratio concepts that we were talking about, where you have a primary set of turns and a secondary set of turns, and you can go ahead and you can actually look at your circuit and say, well, is this consistent with what I expect it to be in terms of voltages, perhaps in terms of the number of turns, although that's much harder and actually much less useful to us. But the concept is that we're going to go ahead and look at how a transformer and what we'll learn in this single phase transformer is it's a three winding transformer, which has three independent windings, but we're going to tap the transformer and we'll have different access points and we'll be able to look at the voltages and see what those voltages are, what we expect them to be. The other thing we're going to look at is the concept of saturation. And the idea about saturation is most magnetic materials or most transformers, motors, generators, that type of stuff, you actually want them to operate at saturation because the amount of material that is necessary to get an operation without saturation would be quite large compared to what is currently required. And you really don't lose much in terms of efficiency when you operate in saturation because it's magnetic energy. It's not electrical energy that creates heat. But the thing is, all our devices, all of our equipment has to work as intended, meaning if I want a transformer to be able to convert 240 volts to 120 or whatever voltage you want, if it's saturated or not, it's got to be able to reach that 240 volts or that 120 volts, whatever you want. So as long as you don't exceed the rating of the transformer, if I'm running saturated, then if I apply a certain voltage on the primary, I should get that expected or nominal voltage on the secondary. And so we'll see how we'll get this particular value or this particular curve. And you'll notice that the applied voltage that we have here, and a better way to say it is the open circuit or secondary voltage, is going to be sort of proportional to the excitation current. But keep in mind, because of saturation, it's not directly proportional because you can see when we get to this little point right here in our curve, right there, that's where we reach the knee point of our curve, where it starts to peel off from being linear to nonlinear. And then once we get beyond the nonlinear region, we now are linear again, but it's in a different slope. So the slope of the line that we can see here is quite steep. Let me go ahead and see if I can draw that here. So this is the slope of the line as compared to the slope of the line here. Whoops. Which what we can see is significantly less steep than we have. And what that means is that to get an incremental change in voltage out of the transformer, we need a lot of excitation current to do that. So the first thing we're going to do is configure the circuit to look like this. So I've already given you the modules, and this is the configuration that I have. You don't need to do it this way, but this is the configuration that I laid out with my power supply and my data acquisition and my transformers. So now with this layout, and I'll give you one more thing because I'm so kind. Look at that, I gave you one connection. And flick that on so that's good. Now, going back to the circuit, what terminals or what numbers do we need? Keeping in mind, we want to apply the rated voltage of this single phase transformer. And if you go back to the transformer, kind of hard to see. Let me see if I can zoom in a little bit. You can see that going across terminals 1 and 2, that it's nominally rated for 120 volts. Okay. So if I wanted to go ahead and connect this power supply so that I'm not exceeding the nominal rating, what windings or what numbers out of the power supply would you use to make sure that you don't get much more than 120 volts? That's a question.
One hot and a neutral.
Say that again?
One hot and a neutral.
Yep, any hot and the neutral. And because I want it to be variable, which is generally the right way to go, I'm going to pick terminal 4. So what I need over here is terminal 4. Now I've got a multimeter here, so I'm going to use my data acquisition. So what terminal do I need to connect this multimeter on? So this is part of the data acquisition to have it configured so that the plus is connecting to the right terminal. What should this terminal number be? Or identifier, if you will. Remember, this is in the data acquisition. So it's over here. So if I want to use E1 to measure, how do I do that here? How do I wire that up?
You'd go from 4 on the power supply to the red of E1 on the DAC.
Yeah, and that's my question, which is I want this to be the red, right, of the data acquisition, and then I want it to come out of the black of channel 1. And you just have to be aware that this is the E1 input. So if you look back at your DAC, I'm looking for E1, so I want the red and the black in the order that I've specified. I also have to do the same thing for the current. This is red 1. And this is black 1. Okay. Now, you'll also notice that I've got some numbers over here. These numbers, 1, 2, 3, 4, 5, all the way up to 9, correspond to the terminals over here. Okay. So there's no electrical connection whatsoever between terminals 1 and any of these in this lineup because it's on a separate coil of winding. So there's magnetic energy that can transfer here, but no electrical energy. And that also applies to 5. So 1 to 5 are independent, as are 1 to 3, but also 3 to 5, because they're on a common core, a magnetic core, but they're not electrically connected to each other. So what I'm showing over here is all those terminals. Now, if you look over here, this is E2, and you are welcome to go ahead and connect this to E2. But one of the nice things about this application is let's turn on a multimeter. Let's bring in our multimeter, because if you were in industry and you were going to try to take quick voltage measurements, you'd grab a multimeter with its probes and go ahead and make your measurements. So I can see if I'm going to be measuring all these voltages here, 1 to 2, 5 to 6, all that stuff, maybe not necessarily the current because I'd have to interrupt the circuit every time, and probably not this voltage here because I'm measuring it. I want to measure that for a purpose later on. But all these other voltages, I'm going to go ahead and use my multimeter because I've got to take so many, it doesn't make sense to de-energize it. So to wire this circuit up using this diagram, I'm going to go 4 to neutral, and I'm going to run one of those wires to channel 1, 1 to for the current, and 1 for channel 1 for the voltage. And then I'm going to connect that for terminals 1 and 2. So I come out of 4, and I can run this to my current. I connect it over here. Now my current has to head back. So I run it over there, and I still need my voltage. And I'm going to wire it like that. So now I've measured, or I'm energizing the transformer. Now I'm going to have to go ahead and measure. And the first measurement I'm going to take is, let's just go 3 to 4. Let's start off with 3 to 4. And it doesn't necessarily matter the polarity. Let's just put 3 and 4 like that. Switch on my multimeter. And now I'm ready to start taking measurements. But before I actually energize my system, I always want to go ahead and make sure I have the metering channels that I want specified. So I'm only using E1 and I1. I can turn off all these other ones. I can see that the meter 1, channel E1 is set up for AC voltage, and meter 7, channel I1 is set up for AC current. So I'm going to flip the switch, and I'm going to turn this up, and I'm going to kind of monitor as I see. Now, why did this stay at 0, 0? Anybody want to help me out?
You're not measuring live, right now. You have to click the little white button right there.
Yeah, I've got to do continuous refresh so that it always adjusts it. So now I'm going to crank this all the way up to about 120. And I'm going to bring this on a different sheet. I'll bring it back over because I can't, I don't want to zoom out until I get 120-ish. Close enough for me. And there's my voltage. Here's my current, my voltage, 120.45 volts, and my current is 28 milliamps. So in your data table, you're gonna put, and I'm only gonna do these first couple for you. So this becomes 28 milli. And this voltage here is 120.4 or 5, whatever you want. And then I'm monitoring with my multimeter. I'm monitoring between terminals 3 and 4, and I see it's 207.9 volts. So I'm going to go back to my spreadsheet, and where I see terminal 3 and 4, 207.9. And now I can go ahead and measure, and another terminal is to go from 3 to 7. Drag that over here, and I get 104 volts. So I'm going to enter that into the data table from 3 to 7, 104.0 volts. All right, I'm going to pause the recording of the video to give you all a chance to go ahead and set up your circuits and do the data collection that you need. So I'll minimize this and show my setup and pause the recording, and then we'll pick it back up when most people are ready to go, unless there's any questions at this point.
All
Any
good here.
question? What's that?
Oh, all good. No questions.
Okay. All right, so I'm pausing the video and giving you, I don't know, people just got to let me know when they are done. So 5 or 10 minutes, we'll check back in. Okay, so hopefully you've done all your results and you have all the voltages over here. Now, I didn't record terminals 5 and 6. Can somebody tell me what they got for a voltage for 5 and 6?
I got 120.
120 pretty well.
120, okay, perfect. So now, do the secondary voltages compare well with the rated voltages written on the front panel? Well, let's look at the front panel. And I've only got 120, 120, 208, and 104. So if I go over here, I see 120 from terminals 1 and 2. Terminals 5 and 6 are 120 because 60 and 60 is 120. And then 3 and 4, right, which is over here, is 104 plus 76, which is 180, plus 28, which should be about 208. I got 207.9, which seems pretty close to 208. And then the last one that I measured over here, E3 to 7. So E3 to 7, 104, as compared to the rating that we recorded earlier. So at least from the data that I collected, yeah, I would say that those compare really well. And now the number of turns, the primary turns, number of primary turns, number of secondary turns. Now we're going to go ahead and do the calculation. So if the number of transformer windings between 1 and 2 and 5 and 6 each have 500 turns, let's go ahead and calculate. So 500 divided by 500, what does that equal? 1. Let's also do 1 to 2 and 3 to 4. So 1 to 2 is 500. 3 to 4 is 865. I have that equal to around 0.57. So do these values make sense? Well, terminals 1 to 2, 3, 4, 5, 6, have a turns ratio of 1 to 1. Isn't that what we have here? We almost have exactly 120 and 120. So we're not perfect, but we're pretty darn close to having what we expect it to be. because the turns ratio should match the same as VP over VS. In this case, VP is 1:2 and 5:6 is VS. Now let's check that over here. 1:2 is 120.4 and 3-4 we said is 207.8. So let me bring my calculator over and let's divide 120.4 divided by 207.9, and I get 0.579, which is pretty darn close to what I have here. So the question is, are these approximately the same? To me, the answer is yes. Questions on that? Any questions on the first part of the lab?
All good for me.
Yeah, Paul, I had a question. When I measured between 3 and 7, for some reason it gives me 0. All the others,
Here's what I
I don't
get.
know why.
I get 104. Is your power switch on?
Yep, yeah, it's switched on. My
Just for giggles. Oh, what are you getting for E1?
oh, that's the input.
Yeah,
120, 120.3.
and you're not getting any voltage here?
Not on that middle one, no.
From 3 to 7. And you've got your meter connected volts to common, and you've switched over to here to volts.
Yep.
Huh. Maybe delete the wires and try reconnecting it.
Okay.
But I can even go opposite way. And click this on. And I get the same voltage, so I can have multiple meters. I can even connect it here. And here. And then turn on my metering. We'll turn on E2. And I'm getting essentially the same voltage, right? 103.9-ish.
Mhm.
So it might be that, maybe there's a gremlin, something didn't like, the way you switch something on or off. Not exactly sure.
Yeah, I'll just play around, see if I can get a value. For
Okay.
some reason, it was only that one. All
Huh.
the others gave me values, but
Yeah.
Okay,
Paul,
so
I have-
now let's delete some wires. First off, I got to top power off the power supply because it's going to drive me bonkers. I'm delete all the wires except the DAC power. And I'm also going to turn off my multimeters because I don't think I need them anymore. And in my next circuit, what is the difference between the circuit in figure 3.3 versus figure 3.4? What's changed? There's one minor change. Still the same transformer, still the same source, but what's changed?
You're now looking at current on the secondary side.
Yeah, and what does that do by measuring the current on the secondary side? In this circuit, you measured voltage. Over here, you're measuring current. What's the internal impedance of a multimeter, voltmeter, I should say? How much resistance is inside here? It's a key reason why you can take any multimeter and you can walk up to any device, and as long as you don't exceed the voltage rating of the multimeter, nothing will happen to you. So what is the difference between the voltage meter and the current meter? This measures voltage, but it doesn't measure current, right? And the reason why it can't is the meter itself when it measures voltage, has a very high input impedance. So essentially no current goes in here, which is what we want, because if we want to measure the voltage, we don't want to put loading on our circuit to potentially change what that voltage would be. So by having this be an open circuit, we are putting basically a no load or an open circuit on this one. Whereas in this case, because we have an ammeter and we want to let current flow to the ammeter, we want as much current as necessary to flow. We don't want to restrict it, because if we restrict it, then again, that changes the loading. So in this case, we are actually putting a short circuit across the output. So our circuit is going to look awfully similar. That goes there. That goes there. That goes there. And I'm going to measure my voltage. And now I'm going to take my terminals 5 and 6, and I'm going to run those through my multimeter, which now has shorted out terminals 5 and 6 on the windings. Okay, so I've just shorted that. And if you look at the schematic, you can see I'm using I1, E1, E2. So I've got to go back up and set my metering up, turn this one on, turn this one off. This is the source voltage. This is the primary current. This is the secondary current. Now, I've got to be very careful, because I'm putting a short circuit on the secondary of the transformer. That's the concept when we talked about full load or load loss tests or short circuit tests. We've got a lot of current potentially flowing in the secondary. So here's what we need to do. We need to make sure that we don't overdrive this transformer by putting too much current in it, because if you look at the nameplate of the transformer, it says, depending on the winding, you can do 0.5, 0.3, or 0.5. So what we're going to do is we're going to limit it even less, and we're going to only drive 0.2 amps through this device. And what I've got to do now is, when I turn this up, I have to turn that up incredibly slowly. So let's turn it all the way down so I don't trip the transformer. So I'm going to have to turn this up very slowly while monitoring my current. So let's minimize that. And let's bring my metering window over here. And this cannot exceed around, maybe 0.21, 0.22 amps, but not much beyond that. So I flip the switch. I slowly increase it. And you can see, just with hardly any movement, less than 5%, I'm already at 140 milliamps. Continue on very closely. Oh, too much. There, pretty good there. So that is the current that I can push into this transformer under short circuit conditions. And that's perfectly okay. And if you remember from the short circuit test, I'm going to get a voltage source that I'm going to adjust the voltage so that I get rated current flowing into the transformer. Well, look how low that voltage is. That winding was rated for 120, but I'm only at 3.7 volts. So now I can go ahead and enter in my primary voltage, which is 3.684. My primary current is 203 milliamps. And my secondary current is 202 milliamps. So now, turn off my transformer circuit, because I really don't want to be running lots of current through this transformer any period of time. I can damage it. So let's go ahead and let's let it cool. Let's shut it off. Now, I know we're doing things with simulation, but the concepts are still valid. We want to make sure that we don't damage anything. So we're going to turn it off. The safest place for this device is when there's no energization. So we're feeling pretty good. Now we have to do a calculation over here. We have to do the primary current, 203 milli, divided by the secondary current. And if we do our calculator again, oops. So I go 203 divided by 202 and 1.005. All right, so the question is this ratio approximately equal to, is NS over NP the turns ratio? Or is it not?
It is, isn't it?
It is, it sure is, yeah.
And they are the same as well. They're both one.
But be careful here though, right? Because this here is not the turns ratio. The turns ratio is A is equal to the number of primary turns divided by the number of secondary turns. But this is NS over NP. Why is that? Well, that's because, remember, the voltage ratio is equal to the turns ratio, but the current transformation is the inverse of the turns ratio. So it's not NP over NS, it's NS over NP. So this one, I'm feeling pretty good at. Now we're going to go ahead and modify the circuit. So my change is that I am no longer going to be on terminals 5 and 6. I'm going to be on terminals 3 and 4. So I switch positions over. And I'm de-energized. So I'm terminal here. Terminal here. Hopefully I don't need to adjust this, but let's go ahead and minimize it and get ready to adjust by bringing up the metering window. And if I flip the switch, I should be at still my value of 0.2. So the voltage is essentially the same. The current is a little bit lower, but not too much lower. And my current for I2, this is the secondary current, is quite a bit less. So let's take a look at the primary voltage. It's 3.688. Whoops. This primary current is 197 milliamps. And this secondary current I have as 113 milliamps. So is this what we expect it to be? Well, let's do the calculation first. So I'm going to divide 113 milli divided by 197, and I get 0.573. Well, the turns ratio for here, 1 to 2 to 3 to 4, was 0.57, which matches that. So this is the primary turns to the secondary turns. But over here, what I measured is the secondary current, right? So I did the secondary current divided by the primary, and I ended up with that 0.57. So let me switch my screen sharing so I can actually write this on pencil and paper. Okay, so we have a secondary current that equals 113 milli, a primary current, and that equals 197 milli. The turns ratio that we were determined in the previous step, so we're going to go I12 to 3,4. That's the actual turns ratio that we calculated. And that one was 0.57. Now remember what that turns ratio is equal to. It's equal to V primary over V secondary, which is equal to A. I primary to I secondary is 1 over A, which means A is equal to I secondary over I primary. So technically, this should be equal to I secondary over I primary. So let's do our calculation. 113 divided by 197. And I said this was equal to 0.57, which checks out, right? Those are the values that I expect to receive. So what we've just confirmed is that when you go from voltage on the primary to voltage on the secondary, you step down in accordance with the turns ratio. But when you go from current from the primary to secondary, you do the inverse of the turns ratio. So that's what we just proved by doing this portion of the lab. Questions on that? Any questions? Should we proceed on?
I'm good to go on.
No,
You're
I'm all
what?
set
You
as
good to
well.
go?
Yep.
Anybody else, or is anybody still working on this?
I'm good to go whenever.
Okay. Unless I hear a nay, let's move on to the last part of the lab. And this is the one where we'll get to do a lot of work. So over here, because we have fancy multimetering equipment, we actually don't need to do that, this part right here. We're going to go ahead and cross this part out. We don't actually need that. So we're going to build our circuit when we're measuring the primary current, primary voltage, and secondary voltage. So I got to go back to my metering circuit. And I'm going to just delete a bunch of wires just because it's easier to see. All right, so the first thing I'm going to do is I'm going to go ahead and set up my current. So you can see I'm going to 6 to 9. So I'm measuring my current into terminal 6. And I'm going to return on terminal 9. So the neutral comes here. So now I've got the ability to measure current, and I've energized the transformer through terminals 6 and 9. Now what I'm going to do is I'm going to measure the voltage across 6 and 9. So here's the voltage. And I'm also going to measure the voltage across terminals 4 and 8. So it's on a different winding. So let's measure my voltage. 4 and 8. And now my circuit is all wired up. Now what I'm trying to do is I'm trying to monitor the circuit to see if the circuit actually saturates. So what I'm doing is as I push this transformer harder and harder, I should start to see that the amount of excitation current, the amount of current that is required to excite the transformer to get it to drive rated voltage greatly increases. So one of the things to note, I'm applying the voltage across terminals 6 and 9. If I look over here, 6 and 9 is only rated for 60 volts, but I'm actually pushing it to 120 volts. So I'm doubling what the nominal rating of this transformer is going to be because I really want to see what the effects of saturation are. If I only ran it, if I ran it across both those windings, I wouldn't necessarily see it. So this is the important part where, because I'm going to be measuring a bunch of points, I'm going to be starting at 10% of position, and then I'm going to move up all the way to 100%. So remember, in multisim, you actually have the ability of doing a data table. So I'm going to turn off I2 because I2 is not being measured. So I'll turn that off. I'll turn on E2 because I'm measuring with E1, E2, and I1. And that's slightly different than in the figure. Because the figure I said E2, E3, but that's okay. You can do E2, E3, or you can do E1 here and E2 here. It doesn't necessarily matter. And now I'm going to go ahead and I'm going to set up my data table. So I'm actually going to start collecting data. So I'm going to bring up my data table. And what I'm going to do is I want to record E1, E2, and I1. So I click this button over here, which tells me which settings I want to record. And I'm going to measure E1, E2, and I1. And now I'm ready to actually start doing some data collection. So let's minimize this. And the very first one that I'm going to take is at 10% voltage. So I'm just going to be ballpark here. I don't have to be perfect, but I'm going to be ballpark. I'm going to bring this metering window down here. I'm going to flip my switch, and then I'm going to go ahead and record this data point. Boom. I've recorded the voltage on both the primary and the secondary, as well as the current. And now once you have it energized, crank that up to about 20%. Again, that's close enough. I'm going to record the data. And now you all get to do all the way from 20% up to 100%, and then get that into a data table. So I'm going to do that in parallel with you, but you can go ahead and you can capture and collect your own data and go from there. So you can just ignore me and you can do your own thing, and I'll just keep cranking this along. And again, you can do your own data stuff. Don't worry about what I'm doing. Let me know when you all have collected your data. Actually, I should pause the recording here. Okay, so now I've got the data, and there's a couple ways to do this. It's totally up to you. You can do a file export. Also, what you can do a Control-C. And then you can paste it over here, and I don't put it in the top column, and I'll show you why in a minute. So I've just pasted those data points there. So this is knob position, right? So 10%, 20, 30, 40, 50, 60, whoops. 60, 90, and 100. And then these are our measurements, which is this is my primary voltage, my secondary current voltage, and my excitation current. So that's a very efficient way to do that. Now what I want to plot is I want to plot excitation current versus the secondary voltage, because if you remember from the lab handout, way here at the beginning, there's a saturation curve, which shows the x-axis being exciting current. And this one, we talked about this being the secondary voltage. So I'm going to go back to Excel, and a lot of people struggle with Excel in lab today. So I'm going to show you how to do it, which is I'm going to select this data, which is my current, hold on to the control button, select this value, which is what I, whoop, not that one. This one, hold on to this one, which is what I want to plot on my y-axis. And then I'm going to want to insert. And if you look at the charts over here, you may not necessarily know. You can actually expand it out over here if you want more detail. But if you look over here, we typically want an XY scatter plot. It's typically what we want. And then it shows you up here in the scatter plots what you want. So you can display with smooth lines, the points and all that stuff. I usually am just going to click here and then I'm good. Now, there's a problem. This curve, and I can double click it over here, is transformer saturation characteristic, right? But that doesn't look like a saturation characteristic. It looks like the inverse of a saturation characteristic. So if I click on my curve, I right click and I select the data. Then when I edit series 1, that's the only data series I have. If I edit it, my X values should be my current. But if you look over here, it's the actual secondary voltage. So I don't want that. I want here. Then I go back and select my Y values, which should be secondary voltage and not current. Now I'm just going to hold my mouse and select those. And click OK. Now that looks like a saturation characteristic with a knee point. Okay. And since we're all engineers, I would like to know what this axis is. So if I click on the curve and I just hit the chart design, I can add a chart element, and I'm going to add an axis title. And I'm going to add one here, which is my horizontal axis. And I'm going to call that secondary current in amps. And I'm going to do the same thing here and adding a vertical axis title. And that vertical axis tile is going to be open circuit voltage and has the units of volts. And that's what my excitation curve should look like. And you can see it's much easier to draw this, you know, including, excuse me, titles and an actual curve title. Makes it look nice. I can have this nice smooth curve where if you try to do this in LV sim, it wouldn't look nearly as good. So now I can go back to my handout. And the question is, does the exciting current increase more rapidly after the rating voltage is exceeded? So the rated voltage for the winding, if you look at it, so our rated voltage is 28 volts. So if we get to around 28 volts, which is right about here, you can start to see that it's starting to peel off quite a bit, right? So I can still get the voltage that get a higher voltage. I'm just really starting to drive it. I need a lot more current to drive that. So the answer to this question is absolutely. It does need that. And does it show that it gets saturated? Absolutely, it does. Now, the last question for 21, and I would do this with Excel, is it's asking you for a ratio of primary to secondary. So it's asking you for the turns ratio. So I'm going to go ahead and define it, EP divided by ES. And then I'm going to just use a cell formula in Excel, where I'm going to take this, set it equal to, and it's going to be this divided by this. And that gives me that first value. If I flip back onto here, and if you notice when I move to the lower right-hand corner, watch how my cursor changes. See how it changes to a smaller one? When it changes that color, now I can click on that and drag it down. And it's going to copy everything in the cell over here, but update it based on the cells that I want. So you remember the one I entered, it was equal to the primary voltage and divided by the secondary voltage, and it used this column data or row data. Now I move to the next one, you can see it automatically went to B3. Now, here are my actual turns ratios. Do you notice anything about the turns ratios?
They're all the same.
Yeah, they're essentially the same. So remember what we said at the beginning of lab, it's pretty darn important for us to be able to operate a magnetic device and get operating characteristics that we want while we're saturated. If this voltage over here, instead of 57.4 was 57.4, Well, look at the turns ratio. It's trash, right? So it's no longer a good result that it's going to give me operating characteristics I want. So I wouldn't be able to use transformers, but because the voltage is in fact that equivalent value maintaining a pretty tight turns ratio, right? I mean, so yes, you do see a little bit of a change, but you know, hardly any, right? It's 3 digits out almost. So you can see that there's not really much of a change. And this is what it's supposed to do. You need to be able to operate these devices up here and still get the operating characteristics that we want. We still want to get around a factor of 2, 1/2. So we want the primary voltage to essentially be divided by 2 or almost 2 to get the results, regardless of how hard we push this current, this transformer. Now, there's a reason, you know, that we can do that, but at some point, we won't be able to get there from here. So if you look over here, and if I drove it over here, which is basically pushing a 60-volt winding at 208 volts, it might not be able to work for us. So if I look at the data here, and I'm just looking at the data, you can see that now I've got 0.9 amps occurrence, and I still have, you know, approximately that 2-to-1 ratio, right? It's close. But the reason why we don't do this is in the lab, you know, we would be putting 0.9 amps of the current, we would damage the transformer. So if you remember, it's rated for 120, rated for where we applied 120 volts more or less. So at 120 volts, more or less, look at the current now. It's 0.454. And if you remember from the nameplate of the transformer, we can run in that third winding, we can run about 0.5 amps without it overheating. So that's the reason why you can drive it to 120 volts, because the current transformer itself is rated for, you know, 0.5 amp. So being able to do stuff like this in Excel is pretty useful. And this is what I'd like to see in your lab submission, a curve similar like this. We're juniors now, at least. So your curves should look to this level with this level of information, you know, including what the current's going to be, the open circuit voltage, and then the saturation characteristics. So telling me information other than just, you know, just giving me data, this is a lot more useful. You can present this to a client, and then they feel pretty confident that the work that you're doing is correct. So the answer to this question is review the data and how does a primary, it stays constant, indicating continued operation during saturation. Guess I have to. So that might be a good discussion point you have. Okay. Questions, because I believe that is the end of the parts of the lab. So any questions for me?
Do you mind posting the working out for 15?
The what?
The solution for 15, how you solved essentially for 15 question 15. Think it
Yeah,
was.
I'll do this. I'll do this if I can get this to work. Oh. Snipping tool is asleep, I guess. I believe I can dump it in the chat. Does everybody have it in the chat now?
Yeah, I got it. Thanks.
Okay. All right, so questions on any of the material in the lab that we've gone through?
You just want our completed
Yep.
lab here plus the data and graph.
Yeah, so the reason why I would include the data is because to answer this question, you just have to, it's helpful to see that table to show that it stays constant or essentially constant. But more importantly, to understand the concept, hey, I can actually operate this in saturation. I still get good results.
Sounds good.
All right, so I'll pause the video and answer any questions people have. If you feel like you've got all the material done for the lab, you're welcome to vacate out, but I will stick around until the last person's there, so. But I may restart the recording if people have relevant questions, so here we go, we will pause now.